Hello AP students. Today's lesson is going to cover the topics found in sections 8.6 through 8.8. Now in our last lesson we were talking about lattice energy and its relationship with ionic compounds. And so as we begin here today, we want to make sure we take a moment to point out the idea that technically it's impossible to have a completely ionic compound based on the definition that we have for ionic character. This is how you calculate ionic character. You take the measured dipole, okay, and then the calculated dipole, divide them and multiply by 100. And so because these bonds are measured in the gas phase, the ions are very far apart. And so there's no way to get a 100% ionic compound character. As you see in this next slide here, these are all our ionic compounds, the common ionic compounds that we're used to talking about. And uh, lithium fluoride here is the highest uh, in terms of ionic character, not the greatest electronegativity difference, but highest in ionic character, but that's because they're such small atoms, lithium and fluorine, okay? Where here, cesium having the greatest electronegativity difference, it's a much larger atom. But the point to be made here is just that based on the definition we're working with now, it's impossible to have 100% ionic character. And there's other complications, like some of our ions are polyatomic ions. There are none of those shown here, but like ammonium, uh, sulfate, nitrate, all those ions are polyatomic. And so to, to deal with these little complicated issues, we're just going to change our basic definition to be an ionic compound is one that can conduct an electric current when it's melted. Okay, so we're going to not worry about the previous definition, and we're just going to base our idea of ionic compounds on this idea. Okay, so just a little note about that. Okay, moving on, we're going to be talking about models now towards the end of this chapter. In our next podcast, we're going to be describing Lewis structures. And remember, models are things that we create from the microscopic world where we can see it to talk about things and study things on the macroscopic world that we can see so that we can talk about the microscopic world. Remember the history of the atom. We couldn't see the atom, but we were just describing it with pictures that we could understand to talk about the basic concepts, the foundations. Okay, so the point to be made here is that models are really oversimplifications. Okay, they're not reality. Oversimplifications, and many times they're not really even actually what's happening. But like I said, it helps us to understand what we can't see. So as we do gain more and more understanding, as the models become more and more complicated, we just modify them. And so it's important to make sure that you understand the assumptions, the foundations that you're trying to show with the model so that you don't use the model wrong. But remember, the goal is to keep gaining understanding and keep building on the models that we have. So if the model's wrong, we can learn a lot more from it than necessarily if it's right. And so we will be talking about Lewis structures using a model, because then it lets us look at the geometry of different substances, which then lets us look at the kind of chemical behavior we're going to see between these different substances. Okay, so the last idea in this podcast is we have another way of finding a heat of a reaction. Remember in our last lessons in thermochemistry, we had two Hess's law type problems to get the heat of the reaction. Well, now we have a third method for doing that. Okay, it's simply working with the bonds of the chemical reaction. Okay, so this is just a quick reminder, when energy goes in, remember, we're dealing with a positive value, and when would energy go into a system? That would be to break the bond. Okay, so bond breaking is endothermic. Always remember that, okay? And then when bonds form as a product, energy is released because, remember, as a compound, they're lower in energy than their individual atoms, and they're more stable, so they release that energy. So forming bonds is an exothermic. Okay, so forming, exo, breaking, endo. All right, so remember those ideas. Okay, so this is basically how it works. This is supposed to be delta H here. Okay, so let's see if I can draw a delta. Delta H, or the heat of the reaction, is found by a summation of the coefficients times the bond energy, okay, times the bonds that are broken. And then we subtract, and again, the summation, okay, times the bond energy times the bonds formed. So, in essence, what I'm saying is we're going to do bonds broken minus bonds formed. Okay? So, here's a typical problem for finding the delta H of the reaction. So then you can tell, is this going to be exothermic reaction or is this going to be an endothermic reaction? So what you have to be able to do is you have to be able to take your compound now and draw it more structurally. Okay, so like C, H, 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 N, triple bond C. Okay, I just drew that out structurally so that you can see what kind of bonds are going to be breaking and what kind of bonds are going to be forming. Okay, so I see some CH bonds, I see a CN bond, I see a triple bond NC, okay, breaking, and then I see over here, this one forming. Okay, so notice it still looks very similar. So actually, these bonds aren't breaking here, and these bonds aren't forming. They're just already there. So we can kind of ignore these guys. Okay? So what do we have? We really have a bond breaking here, and we have a bond forming here. And that's really it, because there's our CN bond. It's still there. So this is the bond that's breaking. This is the bond that's forming. There's only one of each, so we don't have to multiply by more than one, because there's only one bond. So this is a CN, so that's 305. 305 kilojoules per mole minus, because that's the bonds breaking, here's the bond forming, a CC bond, so that's 347. Okay, I'm going to subtract those, and I get, can I do a basic subtraction here? Oh my gosh, 42. Ooh, that was hard. And now it's going to be negative, meaning this reaction is overall exothermic, okay, and that's kilojoules. Kilojoules per mole. Okay, let's see if we're right. And we are. Okay, cool. So let me do another one from the back of the chapter so that you can see maybe a little bit more complexity to it in the basic idea. So I'll insert a clip after this to give you another example. This is one of the problems. I believe it's problem 68 from the back of the textbook, chapter 8. It reads, acetic acid is responsible for the sour taste in vinegar. It can be manufactured using the following reaction. Okay, and then they give us the reaction here. Right, so here's some alcohol, if you remember your functional groups from CP, okay? And then we've got this compound here. They're reacting, and then here we're forming our acetic acid, C2H3O2. And then here's our acidic part of the acetic acid. Okay, and so the question is asking us, calculate delta H for this reaction. Okay, so we in thermochemistry learned how to use Hess's law, and we solved delta H problems using Hess's law. This is our bond energy method, or our third method. Okay, so what we have to do is we have to go through and see what bonds we have that we're going to break, and then what bonds do we have that we're going to form. So the first thing you want to do is draw your structures. Okay, so there's my H's, my CH3, okay, and then we're attached to the O, and then we're attached to another H, okay? And then this one is just straightforward. And then here's our product. Again, there's our three H's, okay, bonded to C, which is double bonded to the O, and then singly bonded to O, and then H. So what do we have? Let's take inventory. So we have 3 CH bonds. We have 1 CO bond, and we have 1 OH bond. Okay, that's that compound. Now let's look at this one. Well, that one's pretty easy. We have 1 triple bond between C and O. Okay, so there's the bonds that are going to break, and these are the bonds that are going to form. Now there's 3 CH bonds again, 1, 2, 3. Then there's 1 CC bond. Then there's 1 C double bond O. Then there's 1 CO bond. And then there's 1 OH bond. Okay? Now we can simply add all these different bond energies up, add all these up, and then do bonds broken minus bonds formed. But I find it easier that since we have similar values or similar bonds on both sides, that let's just cancel those out. Since they didn't break or form, we don't really have to deal with them. Okay? And then it makes calculations much easier. All right, so what do we have? Basically, we have this one bond here, and then we have 2 bonds here. So it's bonds broken minus bonds formed. And I'm purposely just putting the 1 there to remind you that you have to take into account how many bonds. That's the D in the formula. Okay, so here's my bonds broken. So I need to go to my table on page 374 and look up the bond energy for this, get that value for this bond. Okay, and so it looks like it's 1,072 kilojoules per mole. Okay, then I need to go and look up the bonds for this one and this one. Looks like it's 347 and 745. Okay, now I simply multiply those out, multiply those out and add them together. Okay, and so my final answer, negative 20 kilojoules per mole. So that's the basic idea behind calculating delta H using the bond energies. The biggest trick is making sure you draw all the bonds and don't miss any of them. A lot of times, like this bond gets missed, or this bond gets missed. So just be careful, that you don't forget any of the bonds. But there it is. So then basically that's it for this lesson. And like I said before, the next lesson I'll start talking about Lewis structures.